Okay, welcome back. Sharing my screen here. All right, now let's bring up the slides. All right, so we're now learning all about the Java virtual machine architecture and how we're going to generate assembly code for it. And let's continue that. Let me pick up from where I left off Tuesday. So I mentioned code templates. Okay. Oh, first of all, any questions before I go on? The ISA and I are working on the midterms. Hopefully we'll get those graded for you within the next few days. Okay, and then we'll, of course, then post your scores. All right, code templates. Okay, now think back to earlier in the semester when I introduced syntax diagrams. And of course, those diagrams were a way of specifying the grammar of the language. And the way we drew those diagrams made it very easy, based on the diagrams, to design the parser. Okay, so when we hand wrote the first parsers, we followed the syntax diagrams. Then we translate the syntax diagrams into Antler grammar files, and then of course we allow Antler to generate the parsers for us based on the grammar file. Okay. Now in the back end, we're now talking about code generation. Code templates will specify what object code needs to be generated. And in the back end, when we write the visit functions to emit the Jasmine code, the code templates will help us write those code emitters. The same way that the syntax diagrams helped us write the parser. Okay. All right, so I showed you this template for an entire Pascal program. Okay, so this is a high-level template, and you can see that at the top here, the first two lines of the Jasmine assembly code that we generate has to be this dot class public and then the name of the program, and then dot super Java lang object. That basically says that, like all objects in the Pascal or in the Java world, they're all derived from the master object class, and that's all this is saying here. That our program is a subclass of object. Okay. Then in the gray area, this says that we're going to emit code for the various fields of the class. These then, of course, correspond to the global variables of the Pascal program. And it's a gray box because we'll expand this gray box in a later diagram to show what actually goes in there. Okay? Now, in the Java world, every class has to have a class constructor. So, you know, your Pascal program is being compiled or being compiled as if it were a Java class. And so we need a constructor. And this is boilerplate code here. It just make sure you emit this code. And so it could be a bunch of print statements or whatever to emit this code. Okay? Then here, where it says code for methods, this is where you emit code for any procedures and functions in your Pascal program. In the Java world, functions are called methods. Okay, so well, member functions are called methods. And so when you emit code for a Pascal program's procedures or functions, they will be treated as member functions of your class. Okay, and then finally down here will be the code for the main of your program. Okay. All right. So our strategy is that the Pascal program will be compiled into a public class. Okay. All the program variables of your Pascal program will become fields of that class. Okay, you must have a default constructor. Okay, every procedure or function becomes a member function of the class. And in fact, we're going to make it a private static member function. Okay, I'll explain why later. And then the main method, the main of your Pascal program will become the main of the class. Okay, all right. So that is our strategy, and if we make it look as if it were a Java program, then the Java virtual machine will be more than happy to execute this thing once we've generated the assembly code, and then we run the Jasmine assembler and generate the .class file, which is the binary object format for the Java virtual machine. Once it's a .class file, and if we followed this template and everything else was cool, then the Java virtual machine will be able to execute the program. Okay, the Java virtual machine doesn't care really what the source program was, as long as it has a legitimate .class file. Okay. Of course, most .class files started out as Java programs, but in our case here, it's going to start out as a Pascal program, and then of course in your compiler projects, it can start out as whatever language you choose to compile. Okay. All right, so I just mentioned our strategy here, and we follow this strategy to make sure that we generate ultimately a .class file that the Java virtual machine can handle. Okay. All right. Now, Jasmine, the assembly language, has a few quirks. You've already seen the fact that for the loading and storing instructions, there's the regular form, and then there are the shortcut versions of those instructions. The shortcut versions are limited in the range of constants they can deal with, or are limited in the range of slot numbers. Okay, now the slot numbers, remember, are the indices into the local variables array. So every procedure or function that you're executing at runtime causes a stack frame to be pushed onto the runtime stack, and in each stack frame, there's the local variables array where all the runtime values of the local variables and parameters are kept. And then we have to keep track for each parameter or variable what slot its value is in. So every parameter and local variable will have a slot number. Okay. And then each stack frame also has a operand stack, okay, which is where all the computations that take place in the procedure or function, where it takes place. So you will be pushing and popping values on this stack. Okay. All right. So now another quirk of Jasmine that we have to live with is that when we generate code for a procedure or function, we refer to all the local variables and parameters by their slot numbers. Okay, so we don't refer to them by name. Okay. However, if you are generating instructions for any of the program variables, okay, and that would correspond to what I have here, fields. Okay. Those do have names, and you can name them explicitly in your Jasmine program. So if your global variable is named X, then the instruction, the operand, you would say X. Okay. But if X is a local variable to a procedure or function and it's in slot 5, then the instruction would have a 5 instead of X. Okay. So that's just the way Jasmine is. Okay. All right, and we just have to get used to it. Okay. Okay. Now the Java virtual machine can handle various data types. And in Jasmine, each data type has a letter. Okay, and so you're going to see these letters being used. You know, if an instruction needs to do with integer data type, then it would be capital I, or if it's a float, it would be capital F. You know, that sort of thing. Okay, and then some of the instructions themselves, the mnemonics. The first letter of the mnemonic indicates what data type. So you know, I add says that this instruction is for adding to integers. You know, F add says this instruction is for adding to floats. Okay, that's just a naming convention that they used for the instructions. Okay, but then often you may have to specify for an operand separately what the data type is, and then you use these letters for the scalars. Okay. Now, if the data type is a class, okay, then you have another notation. So, for example, if it's a string, okay, so in the Java world, string is fully qualified name is java.lang.string. Okay, but in Jasmine, you replace the dot with a slash, okay? And then because it is a class name, you put a capital L in front of it and a semicolon at the end of it, okay? So here is for a string, here it is for a hash map. And then if you define your own class, you know, say you have a class called Newton, then is capital L, Newton, and semicolon, okay? Now, what about arrays? Okay, well, here is yet another notation. We use an open square bracket to represent an array dimension. So here is a one-dimensional array of string. And so here's Java/lang/string with L in front of it, a semicolon at the end, and an open square bracket. Okay, and then here is a two-dimensional array of newtons, and so we see the two brackets here. Okay, and here is a a three-dimensional array of ints. Okay, well that's a scalar, so we use a capital I, and here's the three square brackets, and then the letter I. Okay, now the I for int is for scalars, not for a class. So there's no capital L and there's no semicolon at the end, just I. Okay. All right. So yeah, it is kind of a bizarre syntax, but that's the Jasmine assembler, and there's nothing we can do about that. All right.
Professor?
Yes.
So this Jasmine assembly language, does it like have like a list of registers or something I can look up or
Okay.
like
The Java virtual machine does not have registers. And so there aren't any registers per se. Now, the lower slot numbers, I think slots 0 through 5, often will have shortcut instructions that refer to those slots. And the shortcut instructions are shorter, and I would assume that they execute faster. So if you want to think of the lower numbered slots of the local variables array to be like registers, I suppose you can. But I haven't seen any code generators that emit code that tries to treat those lower number slot numbers as registers.
all right, because
So
each assembly language has like its own list of registers, and usually that's like where they start,
yeah,
like the basic instructions. But
it's not really dependent on, it's not the assembly language that determines the registers, it's the machine architecture. So if the machine architecture has registers, then in the assembly language, there are ways of specifying the registers, okay? Java virtual machine does not have registers, okay? In actually, that makes it easier for this class, because for machines that do have registers, then we have to deal with, okay, how do we make use of the registers? How do we move things in and out of the registers? And so there's a whole nother set of things to be concerned with. Well, Java Virtual Machine doesn't have registers, so we don't have to worry about it. Okay? If you're going to generate code for any other architecture and it has registers, then you have to deal with knowing which registers to use and so forth and so on. Okay, but that's not going to be a concern in this class. All right, hopefully I answered the question. Okay, so oh, you're welcome. I did show you this. So here is a okay, this is in Java, and it's basically, I'm saying that I have a function that returns a double, is a static, and it's public. Okay, syntax in C++ is a little bit different, but this is Java. And so if we had a Pascal program that had a function that called func that returned the double, we would compile it as if it were this Java. And then when it finally gets compiled down to Jasmine, okay, this is the one line that represents this function header. And you can see now we're using these letters. So the parameters are integer, long, and float. So here's I, J, and F. And then string is a two-dimensional array. So here is 2 square brackets, and the class is Java lang string. So we see the capital L here and the semicolon here, and the function returns double, and so there's a D here. Okay, so yeah, this is what we have to deal with. So when you are compiling a program in Pascal or whatever language you choose to compile, and you have a function declaration, okay, whatever the syntax is in the high-level language, this is what it ends up looking like in Jasmine. Okay, so it's here you get to see the use of these Jasmine type descriptors, these single capital letters. All right, so we go back to our original diagram here. It's a code for fields. Okay, now remember, fields here correspond to the global variables or the program variables of your Pascal program. These are variables that are declared outside of any procedures or functions. Okay, so they're global. You know, they belong to the program, not to any particular procedure or function. And okay, let me get to there. Okay, so we're going to look at what goes on inside here. Okay, so that's what we're going to look at. And so here's a Pascal program, and you can see there's a bunch of variables with different various data types, and these are program variables. They're globals. Okay, and so they get compiled to here. So what you're seeing here is what goes on, is what's inside this gray box here. Okay, and so you can see each one of them is a field. It's private, it's static, okay? And then we are able to use the names, okay? Now, in my code generator, I went to the trouble of alphabetizing them. That's not necessary, but that's what I did. And then we have to specify the data type of each one of these. So you know, character is capital C, integer is capital I, and so forth, okay? So remember that in the Jasmine code, program variables do have their names. Okay. All right. Okay. Now let's take a look down here. Okay. So it's code for the main method. In other words, the main program. Okay. Well, let's see. Okay. So I'm going to expand this gray box, and this is what it looks like. Okay. Well, here's some boilerplate code. Dot method, public static main, okay? This is a one-dimensional array of strings. Okay, so this is, you know, when you're programming in C or C++, you have a character array there to pick up the values of the command line options, and that's what this is. Okay, this a one-dimensional array of strings, and of course main returns void, doesn't return anything, and so there's a v there. Okay, so in Pascal the main does not return the value. Okay, so it is void. Not Pascal, but in Java and Jasmine, the main does not return a value. Okay. All right. Well, I said this is boilerplate code, and you may recall that when I converted a Pascal program over to a C++ program, in the main, I had some code that maintained a runtime timer, because I wanted to print out how long did it take to execute that program. And I want to do the same thing in Jasmine. So whenever I compile a Pascal program down to Jasmine code, I want to have a runtime timer. And so the boilerplate code basically creates some variables to for that runtime timer. Okay, and so I've got a variable called start, end, and elapsed, and they have underscores in front of them to sort of distinguish them from any names that I might, any variable names from the Pascal program. So that's what this is. Okay, and then I invoke a function called now. Okay, and it has no parameters. There's nothing in here. Okay, but the full name of the function is java.time.instant.now, and it returns a time object. Okay, so here's the return value. Okay, don't worry too much about this. This is this is coming out of the Java runtime library, and I said this is boilerplate code, so just spit this out verbatim. Okay, and you'll be okay. Okay, now if your program has arrays or records, okay, we have to have code to allocate those arrays and records, and that's what goes in here. Okay, so we'll look at this box later. Okay, here's the code for the compound statement. So the main is itself one compound statement, and we would generate code for it, and it would be in this gray box. And then finally down here would be the epilogue. Okay, so the last thing you want your program to do is the code that's in the epilogue, and of course, as you can imagine, is basically to print out the how long it took to run the program. Okay, so if we go back to this box, okay, and we expand it, this is what it looks like. Okay, and then we have to expand some other boxes to go even further into more detail. Okay, so this is like back in the syntax diagrams where one diagram would refer to another. So here, same thing is happening. Okay. All right, epilogue. Okay, so let's see what's down here. Okay, well, more boilerplate code, and basically it's to calculate the elapsed runtime. Okay, so in the prologue, we recorded the time the program started, and in the epilogue, we're going to record when the program ended, and then calculate the elapsed time, and then print that out. And so all this code is to do that. And you can see that I'm calling now again here to get the time when the program finished. And you can see there's a call to in between to calculate, well, how much time elapsed in between those two times, and converting it to milliseconds. And you can see there's a bunch of output statements here. Okay, and this is the main one where we're actually print out the elapsed time. Okay, and again, don't worry about all this that looks like gibberish right now. Is boilerplate code. Just make sure you spit this out at the end of your adjustment program. Okay. All right, so we've taken care of And we're looking at the code for the main method, and we've taken care of the header, the prologue, and I just showed you the epilogue. I said we're going to look at arrays and records later. And so, okay, here's where all the executable code goes for the main. Okay. Well, okay. Any questions so far? Okay. I'm just showing you what we have to emit in terms when we compile a Pascal program into a Jasmine program. Okay. All right. Okay, so here again, we're going to look at program variable. Okay, and again, a program variable, we are able to specify the name of the variable in the Jasmine code as opposed to a slot number. Okay, well, program variables have some Jasmine instructions that are specifically for program variables. Okay, so let's say we want to push the value of a program variable onto the operand stack. Okay, and so that is a get static. Okay? Now, why is it get static? Well, it's because when we do program variables, okay, but that's way back. Okay, where do we do the fields? That's where all the dot fields were. Okay, there we go. Okay, they're all dot field private static. Okay, so I chose to make everything static because if we get into object-oriented code, then things get a lot more complicated. And so to keep this class relatively doable, we're making everything static. So we're not taking advantage of the object-oriented features of the Java virtual machine. We're making everything static. Okay, so we compile all the program variables into static fields. Okay? And so therefore, in the code, when we want to access the values of those fields, is going to be a get static instruction. And what that does is that it gets the value of that program field and pushes it onto the top of the operand stack. Okay. And now you notice that to refer to the variable, you have to say the name of the program slash and then the name of the variable. So assuming that the name of your program was test, then you say test slash count, and then you have to specify the data type of the variable. And so if count is an integer, we have to put a capital I here, and if radius is a float, we have to put a capital F here. Okay, so there we go. Okay, and then here's that little table again. Okay. Of course, then to pop off a value from the operand stack and store it back into a program variable is a put static. Okay, so put static says, okay, pop off the value and put the value into a program variable, and so it's put static. Okay, so if we're dealing with program variables, then these are the instructions we would have in our Jasmine code. Okay, get static, put static, and then it's name of the program slash name of the variable space, and then the data type. Okay. Now, of course, once the values are on the operand stack, then you can do iadd and all those instructions that pop off the top two values and add them and subtract them and so forth. Okay, but getting them onto the stack, we do need the get static instruction, and then popping off values from the stack and putting them back into a program variable, then is put static. Okay. All right. So so now that means that when we generate code and we are accessing a variable, we have to look, is that variable local, in which case is a slot number that we have to put in the instruction, or is that variable global, in which case we then use put static or get static and the name of the variable. Okay. All right, so you can see that generating code at a low level means keeping track of a number of details. Okay. Now in our symbol table, remember the symbol table that we built, we do keep track of the level number of the scope level of each variable. So if it's scope level 1, we know that, oh, it's a program variable. I have to use get static and put static. And if it's any higher, then you know that, oh, this has to be a local variable declared inside a procedure or function. And therefore the instructions, I need to use the instructions that use a slot number. Okay, so a few things to keep track of. Okay, all right, so we're down there. Okay, so let's see, code. Oh, okay, now let's look at. Okay, we'll look at this more later. Okay, I'm trying to give you sort of a high level view of things, and what code for methods. So this is where we put the code for any procedures and functions. Okay, and all right, well, here I'm going to blow up this box. Okay, so this is what it looks like for just one procedure or function. Okay, it's going to be dot private static. Okay, we're going to compile every procedure or function into a static method. Okay, the signature, okay, of the function is return type. Okay, now you already saw an example of this back when I showed you this. Okay, here's an example of one of those things. Okay, we have method public static, the name of the function, its signature, all the parameters, and its return type. Okay, so that's what that's what this is. Okay, so code for the local variables. Okay, that basically says you're saying what slot number each variable has. And then again, if we have arrays or records, we do have to allocate data, allocate memory for those. So that will go on in here. And then for the body of the procedure or function, we would have that code here. Okay. And then we need code to return from the procedure or function, and that's the code for return. Okay. Now there is boilerplate code. There is the signature at the very top, or the header, and then at the end we do have an epilogue, and you can see corresponding to the dot method there is a dot end method, and then we have these two limit lines. Now I guess you figured that already, that any thing that starts with a dot is basically not an instruction, but it's a control for the assembler. Okay. Okay. Just a second here. I need to end something that's been running on my machine here. Okay. All right. So boilerplate code. Okay. So here again, I show you this same example. Okay. So this is the dot private static up here. Okay. And well, this was a slightly different example. Here we have, okay, two integers, two floats, a Boolean, and that's a Z, capital Z, a character, that's the C here. We have a vector, and vector is an array of real. And so we have the square bracket and F. And then finally, we have an integer, that's the I here, and this whole function returns a real, and so that's the F here for float. Okay, so example, okay? And then I already showed you these .vars. Basically, it's to specify, okay, what is the name of the local variable or parameter, what is its data type, and importantly, what is the slot number. Okay, so here you see that I has slot 0. Remember, the Java virtual machine automatically assigns the first parameter to slot 0. And then, so therefore, J has slot 1, and X and Y will have slots 2 and 3. So here's 2 and 3, and so forth. Okay, and you notice that vector is data type is a one-dimensional array of float. Okay, now we also allocate an extra slot. So, before I go on to that one. So if length ends up being slot 7, okay, then that means that these local variables, if the last parameter function was slot 7, then n should be slot 8, and sure enough, there's 8, and then 9 and 10. So z is 9, and w is 10. Okay. And then I do allocate an extra slot. Okay, that would be number 11 for the function name itself. Okay, because you recall that the way you return a value of a function in Pascal is by assigning the value you want to return to the function name. Okay, so to make that happen, I do then treat the name of the function as an extra local variable, and so that's why I have a slot 11. Okay. All right, so these .vars will tell you for each variable, each local variable or parameter, its data type and its slot number. Okay. Okay. Now it turns out that these .vars are not necessary. They're really there for you, the programmer, to keep track of the various local parameters and variables, their data types, and their slot numbers. Okay, when you emit instructions that refer to these variables, you're going to put out the correct slot number. Okay, and so it doesn't matter what you set up here. If you're going to put out an instruction that refers to Z, you better have slot number 9 in that instruction. Okay, and then the instruction itself, if it's an instruction for adding 2 integer values, then you better make sure that what's on top of the stack are 2 integer values. And so, as I said, these .vars are not necessary at all, okay? But they're very, very handy to put out so that when you're reading the Jasmine program, when you, the human, are reading the Jasmine program, this will tell you, okay, what slot each local variable or parameter has. Okay. All right, but it's not necessary for the assembler. Okay. All right, and now these slot numbers, where do they come from? Okay, that means that in the front end, okay, when the semantic pass is building the symbol table entries, it can assign the slot numbers. So the semantic pass will say, oh, slot 1, slot 2, slot 3, slot 4, and so forth. And so in the symbol table entry, for each identifier, for each parameter and each variable, we can have a slot number. And so those are assigned in the front end during the semantic pass. Okay? So that's where the slot numbers come from. We have to then make sure that the semantic pass, when it's building the symbol table, is also assigning the slot numbers. Okay. All right, well, here is an expression, and how do we know what Jasmine instructions to generate for an expression like this? Okay, now remember we have a parse tree. Okay, now the parse tree that I'm drawing here is the parse tree that we built by hand at the very beginning of the semester. Now, of course, Antler, the parser that Antler generates, will build a parse tree. It's not all that different from the one that I've drawn here. Okay, but basically, you're going to walk that parse tree. In other words, you're going to be visiting its nodes, and the visit function that you write for each type of tree node will then know what Jasmine instruction to emit. Okay, so let's just take a look at this. Okay, so here's a tree, and I'm showing here a post order walk of the tree. So each of these little numbers tells you what order we're going to be visiting the nodes. So first we visit this one, then we visit this one, then this one, then 4, then 5, then 6, and 7, and so forth. Okay, this is a post order walk of the tree. Okay, so that means that in the back end, when you are dealing with a parse tree that Antler builds, you have to control how you visit the children of the nodes. Okay, and so basically you want a post-order traversal. Okay, well, let's see how walking this tree allows us to generate Jasmine code. Okay, so well, we are visiting this variable node, okay, and we then do remember each tree node will have a pointer to the symbol table entry of the variable, and so when we look up alpha, okay, well actually we don't have to do any lookups, we have a direct pointer to alpha's entry. We discovered that alpha is a float, it's a real, has a real value. And so, and then if we assume that alpha is in slot 0, okay, then we know that, okay, when we visit this particular tree node, we have to emit a float 0. Okay, well, we know we have to emit an F load, okay, to load a float value, to push a float value onto the operand stack. And if the symbol table entry for alpha says it's in slot 0, we know we can emit this shortcut instruction that says, okay, push the contents of slot 0 onto the operand stack. So that's what we do for a variable node. And then number 2 is, okay, it's a constant, okay, and so we know we have to do some sort of load constant. And so here I'm showing not a shortcut instruction, but a regular load constant instruction, and we're loading a floating point version of 3. So here's a 3.0. Okay? And then the next node we visit this one, and it's a variable node, and so it's like the first one, F load, but beta is in slot 1. So here I am emitting a shortcut instruction to push the value, the float value from slot 1 onto the operand stack. And then we do the same thing with gamma. So here is slot 2, okay? All right, now we are going to visit the subtract node, okay? Well, we've been keeping track of the data types, and so we know this has to be a floating subtraction, and so we emit the F sub instruction, which says pop off the 2 float values from the operand stack, subtract them, and push the difference back onto the operand stack. Okay, that's the F sub. Okay, and then we come up, number 6 is a float divide, and that's an F div. Okay, so we emit that instruction. Okay, and then number 7 is an add, so we emit the F add instruction. Okay, and then here we are. Number 8 is integer constant 5, and so we're going to load 5.0. Okay, and then finally up there is a 9. The ninth node that we visit is an add, and so we emit the f-add instruction. Okay, so this sequence of Jasmine instructions will, once we've assembled it and at runtime, will evaluate this expression. So just as we did with the other back-end visit functions, each visit function, knows what to do because each visit function corresponds to a particular type of node. Okay, so whenever it's a variable node, okay, and it's for a real variable, we know it has to be some sort of fload instruction. And if it's a subtract node, we know we have to emit f sub. Okay, if the operands were integer, we would be emitting I sub. Okay, so the visit function has to determine, even though the visit function knows it's doing a subtract, it has to know, okay, are we subtracting floating point numbers or are we subtracting integers? Okay? But the parse tree would have that information because remember that in the semantic pass, we put type information into the tree nodes. Okay, so that information is already in the data type information is already in the nodes by the time the back end gets that tree and starts emitting code. Okay, so it knows that this node has to be floating point, okay, as opposed to integer, and so it knows that, okay, I'm going to emit the f sub instruction as opposed to the I sub instruction. Okay. Okay, so code generation is not that mysterious. Yeah. However, we do have to keep track of a lot of details. As I said, data types, whether a variable is a local variable, in which case we use slot numbers, or is it a program variable, in which case we have to deal with get static and put static calls, and then we can name the variable in the instruction, as opposed to just dealing with slot numbers. Okay, well, was that exciting or not? Hopefully, I didn't give you too much all at once, but there is a lot of details involved. And as you get into this, it becomes easier. So just remember, when the visit function has to know what instructions to emit, and you have to take into consideration data type and whether or not the variable is local or global. Okay. All right. Now let's take a look at some other instructions. Okay. I see that. Okay. Now I'm noticing a bunch of chat messages. Let me take a quick look at those. Make sure they're not. Okay. Questions about registers and okay. Yeah. I think I answered those. Obviously, the Java virtual machine is a stack machine. You have that operand stack, and you're pushing and popping, and some instructions, like f-add, require that the operands are sitting on top of the operand stack, and they'll pop off the top two values, add the two of them, and then push the sum back onto the operand stack. So yes, the Java virtual machine is very much a stack architecture, and is a machine that does not have registers. And so you're basically concerned about slot numbers and what you're pushing and popping onto and off of the operand stack. Okay. All right, well, let's take a look at some branching instructions, okay? So there's a set of instructions, okay, each one of which pops off the top two integer values, compares them, and then either branches or not branches, okay? And so the branch is taken if the comparison is true. So we can compare for equals, not equal to, greater than equal to, less than, or less than or equal to, okay? and this is the integer compare. Okay, and then there's a label that you branch to if the comparison is true. Okay, so these are pretty long mnemonic names. I know that for most of you, assembly language, the mnemonics are maybe at most 5 characters, and here in Jasmine, they are long. Okay. Well, when you write a Jasmine program, the Jasmine assembler is case insensitive when it comes to these instructions. So you could have written this all in uppercase, okay, if you want. Okay. All right, now here's the notation. What are you comparing? You're popping off 2 integer values from the top of the stack, and you're comparing the one below the top to the one at the top. Okay, so that's what this notation is. Okay, so TOS is the value that at the top of the stack, and we put it in square brackets. And then TOS minus 1 is the value that is, I guess, second from the top of the stack. Okay? And so here we're doing the comparison between those 2 values. Now you got to be careful that you get the order right. It's not TOS comparing, well, for equality or inequality, it doesn't matter, but for the greater thans and less thans, you better make sure you're comparing them in the right order. Okay. So you pop off the 2 values, do the comparison based on the instruction, and if the comparison is true, you branch to the label. Okay, so I haven't shown you that yet, but of course, Jasmine instructions can have a label, a statement label in front of them, and then those labels can be targets of branches. Okay. Now, it's important to realize that after you execute any one of these instructions, the top 2 values of the stack have been popped off. So they're gone. Whether or not the comparison was true or whatever, they're gone. Okay, so yeah, be sure you realize that. Okay, okay, so so these instructions, each one of these pops off 2 values and compares the 2 values in this order. Okay, now there's a shorter instruction that only pops off 1 integer value, and it compares that single integer value against 0. Okay, so if it's equal to 0, you branch. If it's not equal to 0, you branch. Greater than, equal to, less than, or less than or equal to 0. Okay, and again, the topmost value is now gone. Once you popped it off to do this comparison against 0, that value is gone from the top of the stack. Okay. All right, so you have 2 sets of compare and branch instructions for integers. Okay, the first set we saw popped off 2 values and compared them against each other. The second set pops off only the top value and compares against 0. Okay. All right. Any questions so far? Okay. Now, what about other data types? Okay, what about longs and floats and doubles and so forth? Well, here's L compare, F compare, and D compare. Okay, and they pop off the top 2 values. Okay, and compare them, but they push back down either -1, 0, or 1 onto the operand stack, depending on the comparison. Okay, if it turns out that it's if the top 2 values are equal, then it pushes a 0 back onto the operand stack. If it's less than, it pushes a -1, and if it's greater than, it pushes a 1. Okay, so there's no branching. Okay, all it's doing is comparing the top 2 values and pushing either -1, 0, or 1 onto the operand stack. So if you want to do a branch, then you follow the compare instruction with one of these guys, and you branch on whether what's on top of the stack is less than 0, equal to 0, or greater than 0. Okay, so if you're comparing longs, floats, and doubles, if you want to do a compare and branch, it takes 2 instructions. The first instruction to compare and leave either -1, 0, or 1 on top of the stack, and then you follow that with one of these 3 instructions that pops off the top value and compares it to a 0. Okay. All right. And remember that if it's a long or a double, that each of the values on top of the stack takes up 2 stack elements. Okay. And so when you call, say, decomp, you are actually popping off the top 4 elements from the stack, because each of the values takes up 2 stack elements. Okay, and then you pop off the 4 values and you push back down one. Well, you pop off the top 4 elements and you push back down 1 element that contains -1, 0, or 1. Okay. All right, so now you know how to compare and branch. Okay. Any questions? Okay. All right. I don't know how many of you know who James Gosling is. He was a senior software engineer at Sun Microsystems, where the Java language was first invented, and he was the lead of that project. And so I have a slide here that says, what would James Gosling do? Okay, and quite often you wonder, okay, here is a statement in my language. Let's say it's a statement in Pascal. What Jasmine instructions should I generate? Okay. Well, now you kind of figure it out by looking at it and saying, oh, well, no, look, there's this kind of expression in there, and oh gosh, look, it's an if statement, so we have to do some sort of compare and branch. So of course you can figure it out. Okay, but another way to do it, okay, and for this works really well for those of you who do know Java, is that you write the equivalent statement in Java. Okay, let's say it's some complicated if statement, and you really want to know what code should I generate for it. So write that statement or the equivalent statement in Java and compile it with the Java compiler. Okay, and then there is a disassembler. Okay, so when you compile your Java program with the Java compiler, you'll get a .class file, and then you can disassemble the .class file and see the Jasmine instructions. Okay, so when you disassemble the .class file, you'll get the Jasmine program, and then you can see, well, gosh, for this complicated statement, this is what the Java compiler emitted, and so that should give you a big hint as to what your compiler should emit. Okay. All right, so I have a little example of doing that. Okay, so here is a silly little Java program. You can see it has a function called test. Well, the program itself is called test with a capital T, and then I have a function called test with a little t. I probably shouldn't have done that, but that's what I did. And it declares a bunch of local variables, and I specify the slot numbers. Now there are no parameters, and so the first local variable could be slot 0, and then they just go consecutively from there. Okay. And you can see I've got a if statement here, and in the true part and the false part, I have an expression. Okay, so there's the red expression and the green and the blue expression. Okay, so let's say that you have a program written in your language, and you've got the equivalent of this if statement in your language, and you're wondering, gosh, what kind of Jasmine code should we generate? Well, then you write the equivalent in Java, have the Java compiler compile it, and then you disassemble the .class file. Okay, so let's do that. Okay, so All right, so okay. So Jasper is the disassembler, and it's yet another program you can download and install on your computer, and then you have this wonderful disassembler. Okay. Now the nice thing about this disassembler is that when it gives you the Jasmine code, it's in a format that the Jasmine assembler can assemble. And so, and that's very useful because you want your compiler to emit Jasmine code that the Jasmine assembler can assemble. Okay. All right, so this is where you get the disassembler. And it turns out that when you install Java, Java comes with a disassembler called Java P, but when you run that disassembler, it prints out the assembly code, the Jasmine assembly code, in a format that the Jasmine assembler cannot handle. Okay, don't ask me why, but that's what happened. And so you really want the Jasper disassembler and not Java P. Okay. All right. So here's the test program in Java, and I've compiled it and then disassembled it. Okay. So here are the instructions. Whoops, the cat just jumped on the table here. Barely kept her from walking on the keyboard. All right, so test.java, that's what this guy is. And Java C is the cat just pushed everything, a bunch of stuff off my table onto the floor. Cats. Anyway, Java C is the Java compiler, and then that results in test.class, and then I run Jasper against test.class, and this is what Jasper puts out. And so you can see that, okay, here's a dot method, a private static test. Okay, that's this guy here, no parameters, and it returns a float. Okay, so that's capital F. Okay, ignore the limits for now. And here are the dot vars. Okay, so you can see that alpha is 0, beta is 1, and so forth. You can ignore this stuff here. It just tells you for what range of instructions is alpha in slot 0. Well, it's for the entire program, so you can ignore these. And then you can see now it's starting to generate the instructions. So it's line 5. Well, line 5, we're initializing alpha to 0. So here we are pushing a 0, a floating point 0 onto the operand stack and storing it into slot 0, which initializes alpha, okay? And we go ahead and initialize all the other variables. There's a dot line, which is another command or control instruction, and it's basically the source line number. So this is, source line 5, 6, and so forth, which is very handy. Okay, and then here line 12. Okay, line 12. Here's where we have to do a comparison. So we're loading slots 4 and 5, which is 40 and 50. Okay, and we're doing well, they're integers, so we can do an if I compare not equal. Okay, if they're not equal, you want to branch around the true part. That takes us to label 26, which is line 16. So we'll branch, if they're not equal, we want to branch to line 16. So you see that here. And then this expression here, okay, I already showed you the sequence of instructions for that. Okay. And then for the line 16, here's a sequence of instructions for that. Okay. There is an F return, which says when you return, the value on top of the stack, operand stack, is the value you want to return. And that return value is pushed onto the top of the caller's operand stack. Okay, so that's how a return value is returned. Okay. And there we go. So here you see what the equivalent Java program looks like. And then we compile it and run the disassembler. And this is the output of the disassembler. Okay. So now you know what the Java compiler puts out for these statements, okay? And then that will give you a good start on what your compiler should be putting out for these equivalent statements, okay? So hopefully on your team, there's somebody who knows Java, but yeah, Java is not that far from C++, so you can probably end up writing a small Java program that's the equivalent of, that contains statements that are the equivalent of the statements you're trying to compile. Okay. All right, that's Jasper. Okay. Any questions about this? Okay. All right. Looks like somebody sent some chat messages. Okay, yeah, the cat. Yes. When I give these talks, quite often the cats are sitting on the table staring at me because they think I'm talking to them, and which is fine, but then sometimes they want to get my attention, and they've learned that there are two things they can do. One is walk on the keyboard. That gets me very excited. And the other is to push things off my desk. And so then I get a mess under the desk. So that's what the cat just did. Okay, one of the two cats I have. All right. Okay, so now what about relational expressions? Okay, I'm showing you the syntax diagrams that we had initially. What about these guys? Okay, what kind of code should we generate if we have a relational expression, okay, in our source file? Okay, and I'm going to give you a hack. Okay, this is a hack, and well, it's a hack because it generates inefficient code, but it's code that's relatively easy to generate. And so I want to show you the easy code generations first, and then later on, if you come up with a better sequence of code, then you're welcome to do it. Okay, so okay, here are two local variables, I and j, and let's say they're in slots 0 and 1. Okay, and we're going to use 0 to represent false and 1 to represent true. Okay, and I'm going to generate code for I less than j. Okay, and therefore the code that evaluates I less than j should leave either true or false on top of the operand stack. In other words, either 0 or 1. Okay. All right, so here's what we do. Okay, so here I and j, first we push them onto the operand stack. Okay, slot 0 and slot 1. Okay, we do a comparison, which pops off the two values and compares them. Okay, now if I is less than j, so here's the comparison for less than, we branch to this label. Okay, and what do we do at that label? We push a 1 onto the operand stack because it was true that I is less than j. Okay, if it wasn't true that I is less than j, we don't branch and we push a 0 onto the operand stack. Okay, but then we have to branch around the code that pushes a 1. And so by the time we get to label 4, there's either a 0 on top of the stack or a 1 on top of the stack, depending on whether I was less than j or not. Okay. So yeah, this is kind of a hack because you can see that where we have to push a 0 or 1, and then there's all this branching around. But as I said, this code is relatively easy to generate, and that's what I'm showing you. So when you look at the code that I generate, whenever there is a relational expression, that means if statement, while loops, repeat statements, and so forth, you're going to see this very hacky code, okay, which leaves a 0 or 1 on top of the stack. And then, of course, if this is inside of if statement or a while loop or a repeat until statement, then you want to do a test to see if 0 or 1 is on top of the stack, and then branch accordingly. And that, of course, is the if EQ statement that says whether or not what's on top of the stack was a 0. Okay, so as I said, yes, you end up generating more code than you would think is necessary to do these kinds of simple comparisons. But I'll leave it to you to optimize this and generate better code, okay? But this code will work. It's just not all that efficient, okay? All right, so here is a code template just for relational expressions, okay? So two gray boxes here, one to evaluate the first operand, one to evaluate the second operand, okay? So I mean, these could be expressions here, and so it's not just I and J. Now in the example that I showed, they were just I and J, so this instruction corresponds to the first box, this instruction corresponds to the second box. We do a compare and branch if true. So here's compare and branch if true to the true label, okay, which in my example was L003. And then after the compare and branch, we push a 0, okay, and then we branch around the true instructions. We branch around down to here, which I'm calling the next label because it's the label of the instruction after the relational expression. And so this is the template, okay, and this is a specific instance of using that template, okay. All right, so now you know how to do expressions. Let me give you a few tips for when you're generating code. I think I've already mentioned these tips. You know, in the back end, you may want to write a function just for generating loading values onto the operand stack. And in that, and you pass it the appropriate parameters so that it will be able to tell, oh, is that variable local? Is it global? What's the data type? Can I use a shortcut instruction or whatever? So you put all those decisions in this one emitter function, okay? And so, you know, all these various things that you can decide when you are emitting code, okay? Now, it's okay in the beginning to ignore the shortcut instructions and always generate the regular form of the instructions, whether you're loading a constant, pushing a constant, or pushing the value of a local variable. You know, you can initially just not bother with the shortcut instructions. Of course, in your final product, you want to use the shortcut instructions as much as possible, okay? All right, so, okay, so loading and storing, you have the same issues, whether it's, you know, local or global, and data types and shortcut versus not shortcut, etc. Okay. And then that's all I have for today. Okay. So again, I barraged you with a lot of new things, and believe me, once you start emitting code, it will start to come together, and you're still finishing up your code converter. And of course, your next assignment will be to start emitting Jasmine code, but we'll put that off until you're done with the code converter. And then your the ultimate project for your for this semester is to write a compiler that emits Jasmine code, a true compiler. And so you can see that you can either invent your own programming language or adopt a subset of an existing language, okay? You have to write an Antler grammar file for it, allow Antler to generate, you know, the parser, lexer, and the parse tree, and then you write several sets of visit functions. You have to write a set of visit functions for semantic analysis, okay? And then in the back end, you're gonna write a set of visit functions for emitting Jasmine code, okay? Which I started to show you here, okay? So that means that you can invent your own programming language, write sample programs in your invented language, compile them, and then ultimately run your sample programs on the Java virtual machine. So that's like the full stack here, from writing a program in your high-level language, compiling it, and actually running it. Okay, so that's the ultimate goal, and a bit daunting, I know, but it is very doable. We'll just take it slowly, step by step, and yeah, at the end of the semester, you will accomplish this. Okay. All right. Any questions? Okay. I see that we've already hit the time limit here. People are sending more chat messages. Okay. There are no questions. I will have my office hour at 4:30. The ISA and I are working on grading your midterms, and I hope all of you have a very safe and enjoyable spring break next week, and we'll see each other again in 2 weeks. Okay. All right. If there are no comments or questions, then I will sign off. Thank you for coming. And oh, I see a picture of Joseph Girani, and he looks like a rabbit. Okay, we're ending here.